going to be our parametric equations and polar equations. So we'll be working with that. So how we define a plane curve. So we have two functions that are continuous on an interval I, and then we are going to look at our horizontal and our vertical components separate from each other. So we'll look at x as a function of t, where t is typically time. So this is not an always, but typically we would use it as a function of time. And so then this is our horizontal, because our x-axis is horizontal. And then y would be defined as a separate function also in terms of t. And so y would be our vertical motion. So these are called our parametric equations. So parametric equations. And then t is specifically our parameter. And so our variable x and y are both dependent on t. So the value of x is dependent upon what t is equal to, and the value of y is also dependent upon what t is equal to. And so t is what we would call our independent variable. Okay. So then as t varies over the interval I, it is called the graph of our parametric equation. And then taken together, our parametric equations and the graph together, both of those pieces, that is called our plane curve, and we would denote that by using C. So we're not going to go into great depth with parametric equations. We're just going to kind of be looking at just different pieces of it. So definition of a smooth curve, so what we would call a smooth curve. So when your curve is represented again by your parametric equations, so x and y, both dependent values on t, it is called a smooth curve if both the derivative of f and g are continuous on I, and then not simultaneously 0. And that will come into play when we do derivatives. So if we looked at when the derivatives are 0 at the same time, we would have 0 over 0, which would be indeterminate. Okay, and so this is true except possibly at the endpoints of I, then we can have different situations. And so then the curve C is called a piecewise smooth. It's called piecewise smooth if it is smooth on each subinterval of some partition of I. Okay. All right, and our derivatives will come on the next page here, so we'll refer back to that in just a moment. So the first thing, so we're looking at is sketching a curve described by the equations x is equal to t squared minus 4 and y is equal to t over 2. So again, we have x is a function of t, right? And then y is a function of t as well. And so t is our independent variable, and it takes on the values from -2 to 3. And then x and y are going to be those values based upon that. And so I'm just going to do a t chart over here. So typically we would have x and y, right? So t is our independent variable. So we're going to choose values of t between -2 and 3. And so I'm just going to do the integer values here. And then we're going to find values of x, and we're going to use this equation here. So x is t squared minus 4. So I'm going to take t and replace it with each of these values. So I'll do -2 squared, which is 4 minus 4, which is 0. And then I'm going to do, so again, I'm just substituting into here. So when I let x equal -1, I would do -1 squared minus 4. So 1 minus 4, which would be -3. And then I'm going to do the same thing again, but instead of -1, I'm going to allow x to be 0. So 0 squared minus 4 would be -4. Substitute in 1, so 1 squared minus 4 is -3. And then replace x with 2. 2 squared is 4 minus 4, which is be 0. And then 3 squared is 9 minus 4, which would be 5. So now I have values of x. So I'm going to do the same thing again, but now I'm going to do it for values to find my values of y. So I'm going to look at y is equal to t over 2. So y is equal to 1/2, right? So half of t. So half of -2 is -1, half of -1 is -1/2, half of 0 is 0, half of 1 is 1/2, half of 2 is 1, and half of 3 is 3/2. And so once I have those values, so even though, let me back that up just a little bit. So now that I have, when I look at my axes, I'm still going to be graphing with an x and y axis. So I'm still going to have my horizontal and my vertical, right? So x is my horizontal movement, y is my vertical movement. And then I'm just looking at my scale here. So it looks like I go positive 5 on the greatest for x. I'm just going to count out to 5 here. And on my negative, it looks like I can go out to -4. So this would be -4 and 5. And then my y value scale is pretty small. So let's see. I guess 1.5 looks like to be my largest. So I'll count out to 2 and then -1. So when I'm graphing, I am just indicating like where that time or when that time occurs, there's my ordered pair here. So in this case, t would not be time because I have -2, but we'll stick with that. Okay, so I'm going to graph the ordered pair 0, -1, again, because there is my x and there's my y. So I'm going to go over 0 and then down 1, and that is my starting point, right? So in this particular moment, because t started at -2. So this would be at t equals -2, right? So that is the start. And then here I'm going to graph that ordered pair, so -3, -1/2. So -3, -1/2. And there's my second point, and then -4, 0. And then let's see, let me write these down as I say them. And then -3, -1/2. So -3, oops, how about a +1/2? -3, +1/2, so somewhere right around there. And then the ordered pair 0, 1. And my last ordered pair 5, 3/2. So over 5, so somewhere right around here. And then these are all equal, so these -2 and 3 would be closed dots. And then I'm going to connect those dots, so it looks like I have kind of a sideways parabola there. And so this is my ending point, so that was ending at at t is equal to 3. So in general, when we're graphing this, we have to, this is like what I wrote here, the t equals -2 and t equals 3. This was just to indicate like where I started and where I stopped. So what does have to happen though is I do have to put direction on here. So when I'm graphing, it's not just plotting a bunch of points, because these points all occurred at certain time values. So this was my starting point here, and then the direction I traveled was along this curve, kind of in a, I guess I could say, a clockwise direction. And so that would be what I need to do. So when I'm graphing and substituting in these values, I do need to also indicate direction by those arrows, and that would be based upon t. So when I'm looking at this ordered pair 0, 1, I know, like, say this was a bug crawling along this line here. So at 0, 1, when did the bug get to that particular point? And that would be at t equals 2 seconds. Okay, so now for here, they're asking me to find a rectangular equation for the above parametric equations. So let me write those. Oops, sorry, my pen got away from me. So I had x is equal to t squared minus 4, and I also had that y was equal to 1/2 t. So the first thing I want to do is recognize that your parametric equations are when you have x and y as functions of t, right? So you have two independent, oops, pretend that's an equals there. Two independent equations, both depend upon the variable t, whereas a rectangular equation is when you have y as a function of x. So the first thing I want to do is, it doesn't matter which equation, but I want to solve for t in one of the equations. So, and it really doesn't make any difference which one you do. I'm going to solve for t in this equation because I can do that just simply by multiplying by 2. So then I would have 2y is equal to t. And then once I have that, my second step would be to now substitute t with the found equation. So the equation you just found. So now I know t is equal to 2y, so I'm going to take that 2y and I'm going to substitute that into this function here. So I would have x is equal to, and then instead of t squared, I would have 2y quantity squared, and then minus 4. And then let me go ahead and square that out. So I would have x is equal to 4y squared minus 4. And then we want to have y as a function of x, so I'm going to add 4 to the other side. And then I'm going to divide by 4 or multiply by a fourth, however you want to write that. And so in this case, I do have a rectangular equation here, but I don't have y as a function of x. So this would be our sideways parabola that you would have worked with in your Honors Math 3 course. And so I can leave it like this because I do have that as a function, or if I did square root it, I would have y is equal to, and it would be plus or minus, right? So it would be plus or minus the square root of, well, let me actually write that out. So the square root of 1/4, which would be 1/2, and then I can't root x plus 4, so I'll just leave it like that. And so then I don't have a function, right, because I have that sideways parabola, but I certainly have a rectangular equation there. All right, let's take a look at the next page. So that's kind of our first look at non-calculus based parametric equations. So now we have to put the calculus spin on it since we are in a calculus class. So this is our parametric form of the derivative. And so when we take our derivative dy over dx, because again, when we're dealing with parametric equations, we have x as a function of t, and then we also have y as a function of t. So this is our horizontal movement, right, side to side, and then that is our vertical movement. So if I want to know the slope, I'm going to take a look at the rate of change of y with respect to t divided by the rate of change of x with respect to t. And then this is provided that we won't be dividing by 0. So, and then I'll talk about the second derivative here in just a moment. Okay, so we have x is equal to the square root of t and y equals 3t minus 1. So if we want to find dy over dx, this is the answer is going to be in terms of t. So keep that in mind. Okay, so then we're just going to take the derivative of 3t minus 1, which is 3, and then we're going to divide that by the derivative, so dx dt, so the derivative of x with respect to t. So then that would be 1/2, and then t to the negative 1/2 power. Okay, so just to make sure we understand that, right? So I just took the derivative of y with respect to t, and that's just equal to 3, and that's where that came from. And then I did the same thing again, but I do it for the square root of t, and that's just the same as t to the 1/2. So that's just power rules. So I'm going to do 1/2 and then t to the negative 1/2, and then that's where that came from. So I have dy dt divided by dx dt. And then, of course, we should simplify that because we certainly don't want to leave that as a complex fraction. So I'm going to multiply the numerator and the denominator by 2. So I would have 3 times 2, which is 6, and then t to the negative 1/2 power. And so that can just pop back up to the top. So that would be just 6 root t, or 6t to the 1/2. Okay, so there's my first derivative. So for my second derivative, so this one throws people for a loop. So I'm just first going to just talk about like the memorizing component, and then I'll talk about maybe trying to understand a little bit as well. So I have, so when I find the second derivative, it means I'm taking the derivative again, right? And so keep in mind that this right here is in terms of t, right? But I need to take the derivative with respect to x. So that formula is, so if you want to think of it as a formula, is we take the derivative that we just found with respect to t first, right? Since it's in terms of t, and then we divide that by the derivative of x with respect to t. Okay. So again, let's talk about just like that process. So I'm taking the second derivative. So I'm going to take the derivative with respect to t of my first derivative, which was this, right? That's what I got. So I'm going to take that derivative and then divided by, so that was this first piece here. So let me, oops, I was trying to erase that. Okay. So this is what I wrote down right here, right? So I took the derivative with respect to t of my first derivative, which is that right there. Okay. So now I need to divide by dx dt. So I need to do that. So then I need to take the derivative of my x, which is root t, with respect to t. And so that's this piece here. So then let's do that. So then this would be t to the 1/2 power, right? So 6 times 1/2, so that'd be 3. Did I not click on this? What is happening? I don't know what happened there. There we go. I think I'm back to normal. Back to normal, people. Okay. So power rule, that's what I was doing here. So 1/2 times 6, so that would be 3, and then reduce the power by 1. So that would be to the negative 1/2. And then down here, the square root of t, so that would be 1/2, and then t to the negative 1/2. And then, of course, that would reduce to 1. So I have 3 divided by 1/2, which is the same as 6. Okay, so now if you're interested in the y piece, so what just happened there? So keep in mind that we are taking the derivative of the first derivative, right? Oops, oh, that should be x. But this is in terms of t, right? So when I take the derivative of this, keeping in mind that we're in that first derivative, that we're taking the derivative with respect to t, right? Because it is in terms of t. And then because of chain rule, we just took the derivative of the variable t with respect to x. So I know we have it divided by dx dt, but that's because we're really multiplying by dt dx, right? Oops, that should be an x here. So when we do this, we're taking the derivative, right, of this in terms of x. And so I just took the derivative, because remember, these are all t variables in here, so those are all t's. I just took the derivative of t with respect to x. And so we're multiplying by that chain rule. So just as like to kind of recapture some of your old stuff. So if we had areas equal to, say, pi r squared, and I want to take the derivative of that with respect to t. So the derivative of a is 1, and I just took the derivative of a with respect to t. The derivative of pi r squared is 2 pi r. I just took the derivative of r with respect to t. And that's exactly what I'm doing here. So I'm taking the derivative of these t variables here, right? And that would be like, say, the 2 pi r part. And then I have to state that I just took the derivative of t with respect to x. And so instead of multiplying by that dt dx, meaning I'd have to solve for t and create this equation, it's just quicker and or easier, more direct, I guess, just to take and divide by the derivative of x with respect to t. Okay, so that was just kind of like the why behind it. So we'll see how that fares. Okay, all right, so arc length, we have done arc length already. So you may want to review your chapter 6, which is from first semester. And so when we took the derivatives of y with as a function of x, this was our arc length formula, right? And this just came from Pythagorean theorem. And so this, again, is from our chapter 6 days. So now when we look at arc length in parametric form, it follows along that Pythagorean theorem a little bit better. So arc length here would be, because we have x and y independent, we need to take the derivative of x with respect to t squared and then add that to dy dt squared. And then, of course, we would take that square root. And again, just kind of like the y behind it just a little bit. So if I have this curve here, right, and I want to know, well, how long is this curve, right? If it were a straight line, which it's not, but if it were, then I could just do Pythagorean theorem, right? I would just do a squared plus b squared is equal to c squared, and it'd be that length. And so integration is the beauty of adding up little tiny things. And so if I were to figure out, well, how long is that? That kind of looks like a straight line, yeah? And I could do Pythagorean theorem and figure that out, right? And then I could take that little section, I could take that little section. So I could take all these little itty bitty pieces, which look fairly straight, like if I zoom in on it tight enough, and do Pythagorean theorem on it, and then find the length of each of those pieces, and then add them up, and I would have a really good approximation of that arc length. Or the power of calculus, when I integrate, right? So when I'm integrating something, I'm summing up, and so here I'm summing up a little baby Pythagorean theorem hypotenuse, right? So this is my a squared plus b squared, and then the square root of that, which is finding me that length. Okay, so there's the y behind it. So let's go ahead and do a problem. So I want to find arc length, so I'm going to use the formula. So s is equal to, and then we're going to integrate from -1 to 0, the square root, and then I need to take the derivative of x and then square it. So I'm going to take this derivative here. So that derivative is 2t, and then I'm going to square it, and then I'm going to go plus, and now I'm going to do dy dt, so dy dt. So I'm going to take the derivative of this now. So that would be 12t squared plus 0, and then squared, and then with respect to t. And then I like to simplify this just a little bit before I type it into my calculator. So that would be 4t squared plus 144t to the 4th, and then with respect to t. And then at this point, we're just looking for setup only, but you can also, if you want to, type it into your calculator and do a value here, but we'll just do the setup only. Okay, and then this is review from chapter 6, so we're going to do the same thing. So also finding arc length, right? So these both are asking for the same thing, but the difference here is we have x and y as dependent variables upon t, whereas here we have y as a function of x, so we have a different formula. So it's still going to be arc length, and our limits are from 0 to 3, right? So from 0 to 3. And then that formula from chapter 6 is 1, because it's dx with respect to x, so dx over dx, so 1 squared. Plus, and then now we're going to take this derivative, so that derivative would be 2x plus 4. And then we're going to quantity square that, and then with respect to x. Okay, and then again, you can type that into your calculator, but we'll just do the setup for this. All right, so that is it for the first part of chapter 9.